What's up? I'm Vin, and today I want to show how to find the area under polar curves. So we're going to go through these three examples, and here's some notes to help us out. Now, this formula for the area under a polar curve with the integral comes from the area of a sector of a circle formula. And that's because the cross sections involved here are very, very skinny sectors of a circle. So the only difference between this formula and this one is that instead of theta, we have d theta, because these are really thin slices. And instead of r, we have r as a function of theta because our radius changes when we're dealing with curves of this type. So this should hopefully help you remember the formula, because in calculus it could be very tricky to remember all the formulas you get. So let's get started. Now for these questions, the best thing we could do first is sketch them. So if we draw this out, what we're going to do is we're going to plug in values for theta and see what is the radius for each theta. Now to start, we could try theta equals 0, and we'll get 4 plus 2 cosine 0, which is 6. Which tells us our first point is going out 6 units in the direction of 0 radians, and we'll just label it as 0, 6. Now the next direction we could look is north in the pi over 2 direction, and cosine pi over 2 is 0, so we would have r equals 4 in that direction, which gives us pi over 2, we have our comma 4 here. Now when we're going in the pi direction, we have cosine pi is -1. So we'll have 4 minus 2 is 2, which tells us we're going 2 units in the direction here going towards pi. So this would be pi, comma 2. And then the last direction we could check here is going south at 3 pi over 2. And at 3 pi over 2, cosine is 0. So we're going 4 units in this direction here, which gives us the 4 major points that we need to sketch this. And this is a convex limasson, which really just means it's going to take the shape of an egg. So this is what our shape looks like, and that's what we're finding the area of. Now, the major idea for these kind of questions is you have to know, when does the loop start and when does it stop? So it started at theta equals 0, but if we were to test out theta equals 2 pi, this would bring us right back to where we started, because cosine of 2 pi is 1, which would give us the coordinates 2 pi, 6. So that's the beginning and the end of our region here, and it's going to help us set up our integral. So what we need to find is 1/2, and our limits are, we have the beginning is at 0, the end is at 2 pi, and then our function of theta is 4 plus 2 cosine theta, and that's what's being squared. So we just have to evaluate this integral. But one other idea we can make use of here is this symmetry, that the x-axis cuts this directly in half. So what we could do instead is we could double this integral but change the limits from 0 to pi, because at pi, if we start here and stop at pi, that's going to give us the area of just the top half of this thing. So all we need to do is just find the area of the top half and then double it. So then that would allow us to set up this integral. We would have 2 times, and now we have 1/2 the integral from 0 to pi, and we have our 4 plus 2 cosine theta squared, which we could expand. If we multiply this binomial by itself, we would have 16 in front, and then we have 4 times 2 cosine theta is 8 cosine theta, but we have 2 of those, so we're going to have 16 cosine theta as our middle term, and then this will end with 4 cosine squared theta. So we just need to evaluate this integral. The 2 and the 1/2 cancel out, and to go from here, the best thing we could do is to probably just find the antiderivative of these 2 terms first, and then use the trig identity for cosine squared to handle this piece. So if we look, the antiderivative of the first 2 terms is going to give us 16 theta plus 16 sine theta, and this is being evaluated from 0 to pi. Now for the other piece, for the last piece here, the 4 cosine squared theta, for that one, we're going to have 4 times, and the identity for cosine squared is going to give us 1/2, and we have 1 plus cosine 2 theta. But now we just have to throw the integral in. It's the integral from 0 to pi. And then we just throw our d theta at the end so that it's technically sound. And 4 times 1/2 is equal to 2. So now we just take the antiderivative of this piece, and we'll be closer to our answer. So what we have first, we have 16 theta plus 16 sine theta. That part doesn't change, and we're going to leave the limits here from 0 to pi. And now the antiderivative of the next piece, we have 2 times antiderivative of 1 is theta, and the antiderivative of cosine 2 theta is 1/2 sine 2 theta. We could have done a u sub there, but it helps to know how to do those antiderivatives quickly because these questions already have a lot involved. So we don't want to have to spend too much time at the antiderivative step. So now we just have to evaluate this and we're done. So if we plug in, now we have 16 times pi plus 16 sine pi, which is 0. So this piece cancels out. And now minus, so this is for this part. We have minus 16 times 0 is 0, plus 16 sine 0 is 0. So this whole second term just cancels out completely. Now for the second half of this thing, we have plus 2 times, and now we've got pi plus 1/2 times sine of 2 pi. Sine of 2 pi is 0, so this goes away. And now we've got minus, we plug in 0, we're going to have 0 plus 0 again. So this remaining terms here at the end also cancel. So then all we're left with here, if we look, we have 16 pi from the part in blue, plus, and the only thing left here is 2 times pi. So that tells us the area of this convex limasson is 18 pi square units. Okay, for the second question here, we're going to start off by sketching the curve. And with this r equals cosine 2 theta, we have a rose curve with 4 petals. And the trick with rose curves, with how to sketch them, is you have to know what to count by when you plug in angles. And the way you find it is you have pi over 2 times the coefficient of theta. And in this case, the coefficient of theta is 2, which tells us that when we make a table of values, we should count by pi over 4. So looking at this here, we'll go ahead and make a table of values. And if we make our table of values here, so I'll just draw it over here. We have theta on the left and we have our r values on the right. So we just go ahead and start counting by pi over 4. So if we go up another pi over 4, that would bring us to pi over 2. If we go up another pi over 4, that would be 3 pi over 4. Then pi, and then this is just going to continue all the way and we'll stop at 2 pi. And I'll explain later why we know to stop at 2 pi, but the key is that you just have to be able to draw this entire rose curve. Now, there's going to be a pattern that we can make use of. That's why we count by pi over 2 times the coefficient of theta. So you're going to see a pattern very shortly. That when we plug in 0, we have cosine of 0 is 1. When you plug in pi over 4, you'll have cosine pi over 2 is 0. At pi over 2, you're going to have cosine of pi is -1. And then at 3 pi over 4, it's going to bring you back to 0. And this pattern is going to continue. We have 1, 0, -1, back to 0, and then we have 1, 0, -1, 0, and 1. Now, with this type of curve, we're just going to go ahead and plot these points. So we're going in the direction of theta, 1 unit. So this is the coordinate. Remember, we're plotting our coordinates in terms of theta and then r. This is the coordinate 0, 1. And now in the direction of pi over 4, that's 45 degrees, or this direction here into quadrant 1, we're going out 0 units. So we're not going to plot anything along this line. We're essentially back at the origin. Now in the direction of pi over 2, that's north, we're going -1, which means go opposite north, we're going south 1 unit. So this is pi over 2, -1. And then after this, 3 pi over 4 is 135 degrees. So we're looking in this direction here, kind of in the northwest direction. We're going out 0, so we're back at the origin. And now pi, we're facing west, and we're going 1 unit. So this would be pi, 1. Now 5 pi over 4 is 225 degrees. So we're looking this way. And remember, this was 3 pi over 4. This is 5 pi over 4. And if we want to write in the other directions here too, this is pi over 2. This is pi. This is down here at 3 pi over 2. But in the direction of 5 pi over 4, we're going out 0. So we're back at the origin. But now when we're facing south, we're going to go -1, which means we're actually going to go opposite south. We're going to go this way, 1 unit. So this would actually be the coordinate for 3 pi over 2 and then -1 here. And then 7 pi over 4 is 315 degrees. That's facing this way. And we're going out 0 units. So we're back at the origin. And then at 2 pi, we're back at this point here. So when you're sketching these, one of the ideas is I'd like to draw in the angles where r is equal to 0. These values are very significant because when I draw in my line at pi over 4, at 3 pi over 4, it essentially tells me the boundaries of my petals when I draw them. Now, you'll notice if I draw a line through pi over 4, it becomes the line at the angle of 5 pi over 4. So I could draw in the line at 5 pi over 4, but I'm just going to be redrawing this line all over again. So these are really the significant values that you need to find your area accurately for rose curves, because when I draw the petals, I can't draw them all the way out of the way like this. I have to keep them within those boundary lines that I drew when I was drawing in the angles. So let's just try to make this as neat as possible. So here's one petal. Now this petal going east, I'm going to have to keep this petal between these two dotted lines here. The petal going south, I have to keep between 5 pi over 4 and 7 pi over 4. And then the petal going to the west here has to be between 3 pi over 4 and 5 pi over 4. So this is what our rose curve looks like, but the goal here is only to find the area of one petal. So we could pick between any one of these petals, but let's say we go with this petal here facing east. Now, one comment we can make here is that 7 pi over 4, we could call it this, or we could call it negative pi over 4, which is more common when you're doing these polar integrals. So the area of one petal, I can now say, is 1/2 the integral from negative pi over 4 to pi over 4, and the function being squared here, we have cosine of 2 theta. And remember, this is being squared. So finding the value of this integral will answer this question. But once again, we could make use of symmetry. Notice that these petals have lines of symmetry. The petals facing the right and left, the x-axis acts as a line of symmetry. So what we could do is, instead of finding the answer to this integral, is we could do 2 times 1/2 the integral from 0 to pi over 4 and just evaluate this integral instead, and we're going to get the same exact answer as we would evaluating this one. And then here we just have to simplify this. This is cosine squared of 2 theta d theta, and then the 2 times 1/2 is going to cancel. So once again, it's much easier to plug in 0 at the end, so anytime I can make use of this symmetry, I do. But if you want to just evaluate this integral, you could. Remember, you could also have done the limits as pi over 4 and 3 pi over 4. You could go from 3 pi over 4 to 5 pi over 4, and so on, but this is the most common one to use. So then here we're going to use our trig identity again. So we're going to have 1/2 when we take care of this square here. And now we're going to have 1 plus cosine, but just be careful. We have to double the term on the inside. Well, we call that the argument. We have to double the argument on the inside of cosine. So when we double 2 theta, we're going to have a 4 theta here. And then this is d theta on the outside. And this is once again going from 0 to pi over 4 now. So once we evaluate this integral, then we're in business and we are finished with this question. So let's go ahead and do that. So for this part here, now we're going to have 1/2, and the antiderivative of 1 is just theta, plus the antiderivative of cosine 4 theta is 1 over 4 sine 4 theta. And our limits are going from 0 to pi over 4. So to evaluate this, now we just plug in. We have 1/2, and we have pi over 4 plus 1/4 sine. And if I do 4 times pi over 4, that's going to give me sine of pi, which is 0, so this part cancels out. And now we have minus 0 plus 0, because sine of 4 times 0 is sine of 0, and that also cancels out as well. So when everything cancels out, all you're left with is 1/2 times pi over 4. So the area of one of the petals of the rose curve is pi over 8. Now, if the question had asked for what is the area of the entire thing, we could just take the area of one petal and multiply it by 4, since there's 4 petals, and that would tell us the area of the entire rose curve, all 4 petals, would be pi over 2. Now for the last question here, we have r equals 1 plus 2 cosine theta, which is a limasson with an inner loop, and we want to find the area of just the inner loop. So let's use technology to get a picture of what this thing looks like. In order to graph a polar curve, we have to go to mode here and switch over from function to polar. So let's scroll over, we press enter, and we're going to make sure we're in radians, which we are. So now we go to the y equals, it's going to say r equals, and for this particular function, we're looking at 1 plus 2 cosine of theta. So when we look at this here, we press zoom 6 to make sure it's in standard mode here. And this is a rough sketch of what our graph looks like. If we want to zoom in a little bit more, we can press zoom number 1. And now this acts like you're cropping a photo. we could place the pointer in the top left corner. We press enter. We drag down and across to essentially crop the photo. And when you press enter again, now we have a much better picture of what this thing looks like. And this will help us answer the question. Okay, so here's our curve, and we want to find the area of just this piece here. That's our goal. So remember before, we said that the best angles to plug in are theta equals 0. And when we plug in theta equals 0, that explains why, if we write our coordinates in terms of theta and then r, that we have 0 and then we have a radius of 3 at theta equals 0. And then at pi over 2, cosine pi over 2 is 0, which explains why we have this point here, pi over 2, and then our radius is 1 at theta equals pi over 2. At theta equals pi, we would have 1 plus 2 times negative 1, which would tell us at theta equals pi, our radius is negative 1. So this point over here is actually pi negative 1. So instead of going west 1 unit, we're going opposite west. We're going east 1 unit when theta equals pi. And then at 3 pi over 2, cosine is 0. So that's this point here. So we got 3 pi over 2. And when we have 1 plus 0, our radius is 1. And then if we were to plug in 2 pi, that would bring us right back. So technically, this is also 2 pi comma 3. So just so we're clear on what's going on here, we are starting at this point here. Then when we draw the curve, it's going in this direction. So it's going all the way around like this. And when it gets to pi over 2, 1 is when it's almost entering the loop. But it goes here, it enters the loop at some point between pi over 2 and pi. So it enters the loop, it goes to the point pi negative 1, then it completes the loop, it exits the loop again, and it completes its full turn all the way around back to here. So this is going to help us out big time, because what we need to be able to find here is when do we enter and exit the loop. But one thing you have to be very mindful of here is that at this point, r is equal to 0 at this location. So just make that a little bit neater. So that's what we're going to make use of here, is we have to know when is r equal to 0. But r is going to be equal to 0 twice. The moment it enters the loop, and then the moment it exits the loop is when r is going to be equal to 0 again. So what we're going to do is we're going to set r, the 1 plus 2 cosine theta, equal to 0. And when we solve this equation, we're going to have cosine theta equals negative a half. And this is going to allow us to find the two values of theta. Now, one thing to be mindful of, we said the first value of theta is going to be between pi over 2 and pi. And if you remember this mnemonic, the ASTC, which tells you where sine, cosine, and tangent are positive or negative, since cosine is negative, that means that our answers are going to be in quadrants 2 and 3, which makes sense because the first one has to be between pi over 2 and pi, which is in quadrant 2. So when we look here, our reference angle for cosine theta equals positive a half would be a reference angle of 60 degrees or pi over 3 radians. But what is the full angle in quadrant 3? Well, in quadrant 3, this would correspond to an angle of 180 degrees or pi radians minus the reference angle, which is going to give us our first solution is 2 pi over 3. And that's going to be our first limit. And then our second limit, this is so this was our quadrant 2 answer. Our quadrant 3 answer is going to be theta equals, and now instead of pi minus the reference angle, it's going to be pi plus the reference angle. So if we write this out, we have pi plus pi over 3. And then think of this as 3 pi over 3 plus 1 pi over 3. That's going to be 4 pi over 3. So the idea is that we have 2 pi over 3, 0 is the first time that this thing enters the loop. And then it exits the loop at an angle of 4 pi over 3. So this is just very, very important. So remember, 2 pi over 3 is roughly here. That's going to be 120 degrees. So it's about here at this angle here. And then we exit the loop at 240 degrees, which is going to be at this angle here. So now we have the information we need to answer this. So the area is going to be 1/2, and now we have the integral going from 2 pi over 3 to 4 pi over 3, and our function of theta is 1 plus 2 cosine theta. And now we have this squared d theta. So evaluating this integral is going to be all we need to answer this question. So now if we want to find the answer to that integral using just the calculator, notice we have our curve already typed in, the y equals. So just remember R1 is our function. So if we go back to the main screen here, the formula is 1/2, so we could write 0.5. And now Math 9 pulls up our integral here, and our limits were 2 pi over 3. So we write our limit 2 pi over 3, and our upper limit is 4 pi over 3. Now we could just retype the function in all over again, but the shortcut is to press VARS. We hit the right arrow, and now we're going to polar here because we wrote this in polar form. And it was R1. Remember, R1 was 1 plus 2 cosine theta. So that's the function here that's going to be squared. So all we're going to do is just attach an exponent of 2 next to it. And now we just write in our d theta. And this is going to give us the actual area inside the inner loop of our limasson. So let's write our answer out. We're going to round to the nearest thousandths place. So we're going to have 0.544 square units. Now let's just say that technology is not an option, that you have to write your answer in simplest radical form. Then we actually have to go through the whole process of taking the antiderivative of this thing. And once again, we're going to make use of symmetry. We said before that the first angle is going to be 2 pi over 3. That's when we enter the loop. And we exit the loop at 4 pi over 3. But just know that when we enter the loop at pi negative 1, that's the halfway point that cuts this inner loop directly in half. So if we once again want to make use of symmetry, we could do 2 times 1/2 and now change the limits. The lower limit is going to change to pi, and our upper limit could stay at 4 pi over 3. Because remember, this thing has a nice line of symmetry on the x-axis, so we could change the lower limit to pi, which essentially cuts this thing in half. So now we just go ahead and expand this binomial squared. We're going to have 1 plus, and we're going to have 4 cosine theta on the middle, because we're going to have 2 cosine theta plus another 2 cosine theta. But then at the end, we have 2 cosine theta times 2 cosine theta is 4 cosine squared theta. So the antiderivative, if we go through it this way, is going to be much like the other questions. It's going to be just as, challenging to do, but the idea is exactly the same. The antiderivative of 1 is just theta. The antiderivative of 4 cosine is 4 sine theta, and the limits are going from, let's just make this a little neater. So we have 4 theta. The limits are going from pi to 4 pi over 3. And now for the next piece here, 4 cosine squared, if we do 4 times a half, that's going to be 2, and we're going to have 1 plus cosine 2 theta. So we're just using this identity once again. And now d theta, and the limits are going from pi to 4 pi over 3. So now we just complete this antiderivative, this piece here. What we're going to have is we have theta plus 4 sine theta going from pi to 4 pi over 3. And now the antiderivative step here, we have 2 times the antiderivative of 1 is theta, plus the antiderivative of cosine 2 theta is 1/2 sine 2 theta. So if we go forward with this here, let's just clean that up a bit. Remember, this is going from pi to 4 pi over 3. Now we just have to plug in. So this one here, we have 4 pi over 3. So we'll put a bracket here. We have 4 pi over 3 plus we have 4 sine 4 pi over 3. And then we have minus pi plus sine of pi is 0. So that's the advantage to changing the limits, is that we at least get a few zeros out of this. And now we got plus 2 times, and we're plugging in 4 pi over 3 for this theta, plus 1/2 sine, and we're going to have 8 pi over 3. And now minus, when we plug in pi, we're going to have pi plus, and half of sine 2 pi is just going to give us 0. So we at least have a few things simplifying. Now, the best way to simplify this from this step, I would combine these two terms. 4 pi over 3 minus pi, or minus 3 pi over 3, is going to be 1 pi over 3. And remember, this is a quadrant 3 angle. 4 pi over 3 is in quadrant 3. Sine pi over 3 is radical 3 over 2. So if we are in quadrant 3, just know in quadrant 3, sine is negative. So we would have minus 4 times radical 3 over 2 in this case. We already combined this pi with the 4 pi over 3, so that's taken care of. And now we've got plus 2 for this part. And once again, combine 4 pi over 3 minus pi. that's going to give you, we're going to have pi over 3 when we combine those. Once again, 4 pi over 3 minus 3 pi over 3 is pi over 3. And now plus, and this I would think about, 8 pi over 3, I would subtract 2 pi, and 2 pi is 6 pi over 3. And that would tell you that this is equivalent to evaluating sine of 2 pi over 3, because this is spinning more than a full circle here. So if you subtract 2 pi, this is a simpler angle to evaluate it at. So I'd have pi over 3 plus 1/2. And if I do sine of 2 pi over 3, that's in quadrant 2 where sine is positive. So now I get a positive root 3 over 2. So to simplify all this, let's see, we have 4 divided by 2 is 2. So we have pi over 3 minus 2 radical 3. And then for when we distribute, we're going to have plus 2 pi over 3. And we're going to have plus, and when I do 2 times 1/2, it cancels. I'll be left with just a radical 3 over 2. But notice we can combine just a little bit more. We can combine pi over 3 plus 2 pi over 3 is just 1 whole pi. So I have pi minus 2 square root of 3 plus radical 3 over 2. And if we wanted to, we could go ahead and combine these into a single term here. Or we could leave our answer like this. So if you wanted to clean this answer up even more, what we could say here is that this is equal to pi minus 4 radical 3 over 2, multiplying top and bottom by 2, plus 1 radical 3 over 2. And then this would be pi, and we'd have minus 3 radical 3 over 2 as a single term here. So this is another way of writing our final answer. Verify that we get the same decimal value typing this in as we did before. Okay, well, this is going to conclude this video on finding area under polar curves. If you found this video to be helpful, please like and subscribe. It helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comments section below. And thanks for watching.